Our last topic of interest is energy transfer, heating, by radiation. That means that essentially light is given off. For an object that's very hot, like the sun or a light bulb, much of that electromagnetic energy will be in the visible range. But for you or me or a house, it's going to be in the infrared range. So this is an infrared picture of a house. The reds and oranges are regions that are hotter, radiating more energy. The blues and greens are regions that are cooler, radiating less energy. It turns out that the rate at which an object radiates thermal energy, gives off heat through radiation, is equal to this formula here. 2 key points: it's proportional to the area, so the more area you have, the more you will radiate, and it's proportional to the temperature to the 4th power. Notice this is not a change in temperature, it's an actual temperature. So this needs to be in kelvins. You cannot use Celsius degrees or Fahrenheit degrees. You can use Ränkenes, but we won't be doing that at all. These other 2 things are constants. The E is the emissivity. It's how good of a radiator and absorber a material is. That can range from 0 to 1. For a mirror, it's nearly 1. For a black object, it's nearly, for a mirror, it's nearly 0. For a black object, it's nearly 1. That's why emergency blankets are mirrored. They reflect all of the radiation and energy back at the person. They don't absorb any of it. And this term here, sigma, is known as the Stefan-Boltzmann constant. For our purposes right now, it's just a value. It's 5.6703 times 10 to the negative 8 watts per meter squared, Kelvin to the 4th. At moderate temperatures like you and me, doesn't become terribly big. At temperatures like the sun, a great deal of energy is lost through radiation. Now, if you're out standing nearly naked on the beach, you're going to be losing a lot of energy from radiation. But you're also going to be absorbing radiation from your environment. So you'll be radiating this way, but you're going to pick up energy from the environment. And you'll pick up energy from the environment based on the same formula. Sigma, emissivity, area, T to the 4th, but whereas this was your temperature, or the temperature of the radiating object, this is the temperature of the environment. So you'd pick this much up from the environment, you give this much off, the net is right here. And here we've listed absorption first to say this will be positive if you're gaining energy. If you're losing energy, if you're radiating more than you're absorbing, this will end up being negative. The sigma, the emissivity, and the area are all the same for both absorption and emission. The only thing that's different is your temperature and the environment's temperature. As a result, we've got temperature of the environment to the 4th minus temperature of the radiating object to the 4th.